Before transformers revolutionized AI, recurrent neural networks, or RNNs, were the standard. But they had a major flaw: sequential processing. Information had to flow step by step, creating a bottleneck where long-range context was often lost. Transformers solved this by processing the entire sequence at once, creating direct connections between every word. At a high level, the original transformer consists of two main stacks, the encoder on the left and the decoder on the right. The encoder processes the input text to understand its meaning, while the decoder takes that understanding to generate the output, one token at a time. Note how the encoder's output feeds directly into the middle of the decoder. Computers don't read words, they read numbers. First, we tokenize text into smaller units. Hello world might become 2 tokens. These are converted into unique IDs, which are then used to look up dense vectors called embeddings. These vectors represent the semantic meaning of each word in a multidimensional space. Since the transformer sees all words simultaneously, it has no inherent sense of order. To fix this, we inject positional encodings. These are specific wave patterns added to the word embeddings. Using sine and cosine functions at different frequencies, they give the model a unique signature for every position in the sequence. Now for the heart of the system, self-attention. Think of it as a spotlight. When processing the word bank, the model needs to know if we mean a riverbank or a financial bank. Attention allows the model to look at other words in the sentence, like money or river, to clarify the context before moving on. Technically, attention works like a database query. For every token, we create 3 vectors: a query, a key, and a value. We calculate these by multiplying our input vector by 3 separate learned weight matrices. The query is what you're looking for, the key is what you match against, and the value is the information you extract. To decide how much focus to put on each word, we take the dot product of the query with all keys. This gives us a score matrix. We scale these scores down for stability, then apply a softmax function. This converts the raw scores into probabilities that sum to 1. These are our attention weights. The result is an attention map. Here you can see a real example. Darker squares mean higher attention. Notice how the model learns grammatical relationships automatically. It's not just distinct words anymore. It's a web of relationships. Finally, we take these attention weights and multiply them by the value vectors. This creates a weighted sum, a new representation for each word that is now context-aware. The word bank is no longer just bank. It's financial institution, because it absorbed information from the word money. One attention mechanism isn't enough. We use multi-head attention, running this process 8 times in parallel with different weight matrices. One head might focus on grammar, another on vocabulary, another on position. We concatenate their outputs and project them back to the original size, giving us a rich, multifaceted understanding. Let's put it together into a single encoder layer. The input flows through the multi-head attention, then into a feed-forward network. Crucially, after each of these sublayers, we apply a residual connection, adding the input to the output, followed by layer normalization. These residual connections, or skip connections, are vital. They create a highway for gradients to flow backward during training, preventing the vanishing gradient problem. Without them, deep transformers would be impossible to train. Layer normalization stabilizes the network. Unlike batch norm, layer norm works on each token independently, normalizing its features to have a mean of 0 and variance of 1. This ensures consistent signal magnitudes throughout the deep network. The feed-forward network is applied to every position identically and independently. It projects the vector to a higher dimension, typically 4 times the model size, applies a ReLU activation, and projects it back down. This adds nonlinearity and capacity for complex processing. Moving to the decoder. It looks similar to the encoder but has a critical third sublayer, cross-attention. Also, its first self-attention layer is modified to be masked. Let's see why. During training, we feed the target sentence into the decoder. But we can't let it cheat by seeing future words. We apply a causal mask, setting attention scores for future positions to negative infinity. This ensures position 4 can only attend to positions 1, 2, and 3. In the cross-attention layer, the magic happens. The queries come from the decoder, what I want to say next, while the keys and values come from the encoder, what the input meant. This is how the translation or answer is grounded in the source text. The final decoder output passes through a linear layer that projects it to the size of the entire vocabulary. A softmax function then converts these into probabilities. We select the word with the highest probability as our next token. Training uses, teacher forcing. We feed the correct previous words into the decoder and ask it to predict the next one. We calculate the cross-entropy loss between the prediction and the actual word, then use backpropagation to update all weights. We don't always use the full architecture. Encoder-only models like BERT are bidirectional. They see the whole sentence at once. They are perfect for understanding tasks like classification or sentiment analysis. They are trained by masking random words and guessing them. Decoder-only models like GPT are autoregressive. They generate text one token at a time, predicting the next word based on history. They are the standard for text generation and chat applications. Finally, encoder-decoder models like T5 or BERT use the full original architecture. They excel at sequence-to-sequence tasks like translation or summarization, where you need to heavily process an input to generate a new output. Transformers succeeded because they handle long-range dependencies, and, crucially, they are highly parallelizable. Unlike RNNs, they can use massive GPU compute efficiently, allowing us to scale them to billions of parameters. The original paper used specific numbers. D_model of 512, 8 attention heads, and 6 layers. These parameters determine the model's capacity. Modern LLMs just scale these numbers up significantly. And that is the transformer. From embeddings to multi-head attention, residuals, and layer norms, every component plays a vital role in the AI revolution we see today.